Welcome back, everyone. And in this video, we want to take a look at the loss functions that we use to calibrate our neural networks. Because in the previous videos, we have seen how we can generate outcomes or output predictions from neural networks that fit to the task that we have. So either regression type problems or classification problems. In the last video, at least hopefully got a glimpse how the gradient descent method works. As I stated before, it is not important for you to understand this fully because you do not need to do this manually. But I think it is very important to at least gain the intuition behind it, so that you understand how your neural networks are going to be calibrated by the packages that we are using. And in this video, we want to focus now on the so-called loss function. Loss functions are, as I already mentioned, some form of feedback, a feedback that tells you if the current prediction of your neural network for a specific observation is rather good. So typically this means if it is close to the actual realization or if it isn't. And we do not estimate our neural networks with perspective on a single observation. We do this usually on a training data set. So usually the loss function is an average of individual loss values that are determined for each observation. And now, depending on the task we're facing, again, here we need to distinguish between regression type problems and classification problems. We need to choose different loss functions. But the idea here is pretty simple. A loss function is something which fits to the task. So for instance, for a regression type problem, we have numerical estimates, or we want real valued numbers as outputs from our neural network that are then compared to real valued numerical numbers which we observe in reality. So for instance, we may want to estimate the value of a house, and we get some information about the house, and then with this information we make a model that predicts the value of the house. And now we have two values, our prediction of the house value and the actual house value that we may observe at the real estate market. And of course we want these values to be close to each other, and to measure how close they are, we calculate the difference between those values. But as we do this for many observations, just summing over these differences, because sometimes they may be positive, sometimes they may be negative. Both cases, positive and negative deviations, mean that the prediction is not exactly as the actual realization. So as we are summing, we do not, these effects could then equalize each other. So, and we do not want this because, either positive or negative observations are bad, so to say, because they signal that the prediction is not accurate, and at least not to 100%. Now we can use either absolute values or squared values of these differences. And due to mathematical attributes, one rather prioritizes here to use the squared deviations. So for regression type problem, an appropriate feedback function is to use the squared deviations, as you can see here. And usually, either we sum these up or we average those. Here we average those, but to keep it general, I choose to you can weight each observation with a different weighting. If you calculate the average as you're used to, then you would use equal weightings. But to keep it as general as possible, of course, then you may weight each observation as you desire. For instance, if you are interested in focusing with your predictions on a certain area, then you may weight observations from this area higher than the remaining observations. Okay, but that's not the important part here. The important part here, for regression type problem, we use the squared deviation as a loss function. And also, what's important here is, always remember, each prediction depends on, of course, the architecture that we are using for the neural network. But given this architecture, it only depends on the parameters, so the weight and the bias terms of our neural network. And by choosing different values here for the weight and the bias terms, of course, our predictions are changed. and we want to change the predictions by choosing weights and bias values in a way that they are possibly as close as it can be to the real observations, but not only for a single observation, so for all observations. So that is why we're using the squared deviation of the loss function for regression type problems. Then this can be solved, like we have this minimization problem in order to choose the best possible parameter estimates given these data observations by minimizing the mean squared error or the weighted squared error. And this minimization problem is solved by gradient descent methods typically. I mean, for a traditional linear regression model, there is an analytical solution available, but usually the more complex our models get, these analytical solutions are not available anymore, and we need to use numerical optimization routines in order to solve this problem. And also the good news is we do not really solve this problem because the package that we are using will solve this problem, but at least we should be aware of it, what it's doing. And it's doing a very, like the models that we will use, they do a very efficient and sophisticated way of gradient descent. Okay, so let's just skip these slides here. They are more or less just, again, the explanation for the gradient descent method, assuming a very simple regression type problem, as we already experienced in the last video. And that's it, what you need to know for regression type problems. Okay, so first step, you need to understand what a neural network is in terms of how are neurons generated, how are output predictions generated. Then you need to understand, okay, it depends on a set of parameters. What can we do to best calibrate these parameters? We want to calibrate the parameters in a way that they minimize the loss function, and minimizing the loss function is chosen in a way that it means generating accurate predictions. So the loss function is our way to define what are accurate predictions, okay? And this now brings us to the question, what loss function should we use for classification problems? And as for the regression type problem, there may be different choices. You know, for the regression type problem, we are not bound to using the square deviations. We could also use the absolute deviations or maybe something else, but like the square deviations are the common choice because it's a convex function, and so we can more or less surely rule out the possibility for creating bad optimization results, you know, like finding only local minimum and so on and so on. And the same holds true for classification problems. There are different choices which function we could use, but here we will take a look at the one that is, I would say, most popular, and that is cross entropy. And without going too much into detail here, also details that I am not fully aware of, to be honest, I think the best way to understand what's happening here and how this loss function works is to take a look what it does, how it compares the prediction with the actual realization. And I think this is quite intuitive for the cross entropy. And as I define it here, it is really a general concept. So sometimes you may see that people distinguish between the binary cross entropy and the cross entropy in general, or categorical cross entropy. Even Keras or TensorFlow does that. But the math behind it is the same, only the way how they define it, how to calculate it is different, okay? So let's take a look at this here. So first, what the loss function for classification problem does is to compare the probability prediction for the category that we are actually observing, okay? So assume, for instance, we have a binary classification problem, and we have the effect coding and encoding that we defined earlier. So that means the target variable here is a vector with dimensionality 2. So here in the first position, this is a value which is equal to 0 if observation I does not belong to category 0, And if it belongs to category 0, then this will be 1. So it's either 0 or 1, and this is all 0 or 1. But it's either here 1 or it's here 1, depending if it's category 0. So let's define category 0 to be a male person, and like if it's a female person, then it's category 1. Okay, so this one is to express if it's female or not. So if it's not female, then this will be 0, and this will be 1 because we have a male person here, and this defines if it's a male person. And if it's a female person, then this value will be 1, and this value will be 0. Okay. And now, in this example, obviously our target is to predict if it's female or if it is a female or a male person. Okay, so we will have a probability vector, a vector of probabilities. The first one defining the probability for being a male. Okay, I think I messed this up. So again, if male is 0, woman is 1. Okay, so this is 1 if it's a male person or 0 otherwise, and this is 1 if it's a female person or otherwise. And so this is the probability here, the estimated probability of the model if it's a male person, and this is the probability that the observation I is a female person. Okay, so if we multiply this, then this leads us to this expression here, and as this is encoded only in 0 and 1s, only one of these two terms will remain. Okay, so if it's a male person, then this is set to 1 and this is set to 0. So this here is lost, so to say, and what remains is only the negative log of our probability estimation that it is a male person. If it's a female person, then this is 0, and this here for first expression is lost, so to say, and this one is set to 1. Okay, and so minus 1 times a log the probability estimate that it is a female person. Okay, so basically what this does here is just that you always get the minus the log of the probability estimate for the actual target realization. So the actual target realization here is either a female or a male person. And if it is a female person, then we want to take a look if our model is able to generate a high probability estimate that it is a female person. Okay, if it is a male person, then we only focus on the question if our model is able to generate a high probability estimate for a male person. We will take a look at this, I think best now really with a short example I'm writing down. So let's just go over to this. I think it makes it more clear than just explaining it here. Okay, so let's make this more intuitive by taking a look at a real numerical example. So assume that we have two different categories that we want to predict. So if it's a male person or female person. So our general target variable is either 0 if male or 1 if female. If we one-hot encode this, this means we have, for instance, for a male person, a vector that looks like this. So this is for the first observation our one-hot encoded vector, and if it's a female person, then it will look like this. Now assume that we have already a model that predicts the probabilities. Okay, so here for the first observation we have the probability prediction, which is 1 minus this value, and the other one is this value. And also for the second observation we have the same, but we have for each observation specifically different probability estimates if it's a male person or if it's a female person. Okay, and now So for instance, for the first observation here, if we, like the what we will use for the loss function is minus log of probability. So that is minus log of 1 minus the probability estimate that this is a male person, and we have minus log, minus log that is a female person. Okay, so this is our probability vector, and that we will use as a loss function. So here, this is the loss function. Okay, now if we calculate the dot product of this vector and minus log of our probability vector, let's make this more clear by using the symbol, then what we get is, if it's here, like we have the example with a male person, then what we get is 1 times minus log of the probability estimation that it is actually a male person, plus 0 times minus log that it is a female person. Okay, and so what remains is minus log of the estimate that it is a male person. So that here is the probability estimation that we think regarding our model that we actually have a male person here. Okay, and in the same way, if we do this for the second observation, so if we do it for the second observation here, you can check for yourself if you're able to do this. What's left here is minus log that this is actually a female person. Okay, and now let's just, it doesn't matter if we use the first or the second example. So this should show you that the way how we define it, so like using this one hot encoding and this vector notation that we use here, it's kind of an elegant way, I would say, that we restrict the loss, or that we, not restrict, but that we only keep the loss values for the actual categories of the target variable. So in our example here, the first observation is actually a male person, and the second observation is actually a female person. So we want to focus our model that we generate accurate probability predictions for the actual categories. So regarding the first observation, we want our model to generate a real high probability estimate that this observation is a male person. But for the second observation, we want our model to generate a high probability estimate that this is a female person. Okay, and these are the values that are, so for the first observation, the probability estimation for being a male person goes into the loss function of the overall model, and for the second, regarding the second observation, the probability prediction for being a female person goes into the loss function. Okay, so we are basically using here, so the overall value of the loss function here would be the weighting for the first observation times minus log of the probability estimate that this is a male person, plus the weighting for the second observation times minus log that this person is female. So that will be the loss function value here. And now if we, for instance, just take a look here graphically. So if you calculate here just the probability estimate, so here the probability, or not estimate but prediction, here we would say this is equal to 1. Here we start at 0, and here we only have minus log of the probability estimate. Then you will find that this looks something like this, okay? And so this means if our probability prediction for the actual category, so here for the male person, that's outputted by the model is already really high. So for instance, assume for the first observation, we would generate a probability prediction that this is a male person, which is 0.9. So we would end up here. And the corresponding loss value seems to be comparably low as compared to, for instance, if we would predict a probability prediction that is, I don't know, 0.2 or something. So then we would this loss value here. So our aim is, of course, to generate a probability prediction somewhere around here, because this would lead to the least possible loss value for this observation. So here, maybe to make this more clear, let's not write here probability prediction. Let us write this is for the first observation. So this is 1 minus p, and then a 1 in the subindex because it's the first observation. And then here for the second one, it looks exactly the same, but here we have the probability estimate for a female person, and again here we simply have minus log of this probability estimate, and again it looks like this. And again we hope that we aim, or that we succeed in generating a model which for the second observation would generate probability predictions for being female in the area around here. So again here, like with high probability values. So, and this is monitored by the parameters of the model. So the parameters of the model will be altered or changed during the optimization routine of gradient descent, with the aim that we generate high probability predictions for the actual categories that we're observing for the target variables. I know that this may still sound confusing now, but if you think about it, it is very intuitive, okay? But let's go back to the slides. And that is, so I think it's really intuitive, because what we really only do here is that if we in reality observe that this is category 1, then we want set the parameters of the model that for this observation, the probability prediction that it is category 1 is supposed to be very high. And if for the next observation is in reality category 3, then of course we want a model that generates a probability prediction that with a high probability mass that it is category 3, okay? And this principle is very general and cannot be used only for binary classification problems. It also can be used if you have classification problems with more than 2 categories, because nothing changes when we still stick to the notation that we use here. So if we have higher dimensions, let me take a look. Okay, I didn't write this down here, but it's still the same. So if we have 3 categories, then what we do here is we have 3 variables and we have 3 probability predictions. But when using the dot product, the only thing which remains for calculating the loss function value is the probability prediction for the actual category that we're observing for this observation. And the higher our probability predictions are for the actual categories that we are observing, the better our model is. And we try to monitor and do this not for a single observation, but for all observations that we have in our data set. And that is why our loss function is again a weighted sum of the minus the log of the probability estimates for the actual categories that we are observing. Okay, sounds complex, but if you think about it, or if you give it a minute or two, I think you will be convinced that it is quite intuitive to use this loss function here, okay? Good, so this brings us to the end of this video. Summing up, you only need to know that using a regression or like a regression model, or if we have a regression type problem, then the mean squared, so like the weighted sum of squared deviations between predictions and actual realizations is what you need to know, what you need to use as a loss function. So this is the appropriate feedback for regression type problems, and the cross entropy function is the loss function that you need to use for category classification problems. And yeah, so I think that sums it up, and now you basically need to know what everything you need to know, at least from in a broader sense, for defining your neural network. Okay, so you need to know how the architecture of the neural network works. You need to understand that the parameter, or like the predictions depend on the parameters, and the parameters are calibrated by minimizing a loss function. And you need to know that how to choose the appropriate loss function regarding the task that you are facing. And if it's a regression type problem, then use the squared deviations. If it is a classification problem, use the concept of the cross entropy function. Okay, good. So in the next video we will take a look at some fundamental concepts before we dig deeper into the different architectures of neural networks. But yeah, for the moment, have a good time, take care, and see you in the next video. Bye bye.